in this talk. So I've been working on sign networks and as you know, based on the theory of structural balance, when we have these four conditions in a sign network, it's called a balanced sign network or a balanced graph for our purposes. So in this example, we can see that enemy of an enemy is always a friend, friend of a friend is always a friend, and the other two conditions are also satisfied. Therefore, this graph is balanced. This other graph, for this one, we have several counterexamples showing that this is not balanced. For example, George and Mike are enemies, but they are both friends of Sarah, which is not consistent with the conditions of the theory. So it's not balanced. But the key motivation for our work is that for many of these sign networks that are unbalanced, there's only a few edges whose removal results in total balance. And in this example, while we had several counterexamples, several unbalanced cycles showing that it's not unbalanced, but in terms of how many edges can be removed to get a totally balanced graph, there's just one edge. So if we can somehow negotiate to destroy this friendship, everything becomes balanced. So here is the notation we're going to use. We represent the graph with G, set of vertices with V, and set of edges with E. We have sets of positive edges and negative edges with E plus and E minus. So we need to define the frustrated edge. So the edge we saw, the friendship between those two people, is essentially a frustrated edge. So when we have a node coloring like X, where Xi represents, where Xi is a binary variable representing color of node I, then a positive edge with two different endpoint colors is frustrated, and a negative edge with the same endpoint colors is also frustrated. So let's see an example. We have a sign graph. Solid lines represent positive edges, dotted lines represent negative edges. If we color the nodes like this, we're going to end up with two frustrated edges. The edge between 0 and 2 is positive with different endpoint colors, and the edge between 2 and 3 is negative with the same endpoint colors. So these two are the frustrated edges. But if we color the nodes like this, we're going to have just one frustrated edge, which is the edge between 1 and 2. So the connection between frustration and balance is that there's a node coloring that minimizes the number of frustrated edges. And this minimum for a balanced network is 0. For an unbalanced network, this minimum is strictly positive, is strictly greater than 0, and we represent it by L of G, because it's also referred to as line index of balance by Harari. So we need a binary variable to represent whether an edge is frustrated. So for edge ij, when we have xi and xj representing colors of the endpoints, fij is a binary variable which shows whether the edge is frustrated or not frustrated. So we can use this to develop a mathematical programming model. Let's see another example. For this balance graph that we have on the left, we can color the nodes like this, which leads to all edges being satisfied or not frustrated. But for the graph on the right, the best coloring we can come up with is this, which makes this edge frustrated. So here is the problem definition. We are looking for the minimum number of frustrated edges over all the node colorings. So when we have n nodes, there are 2 to the n colorings. So we are dealing with an exponential space for our optimization model. The reason why we want to calculate this is because it shows how many edges the network is away from total balance, but it also has several applications in different disciplines, in non-materials, physics, biology, finance, and electronics. So it's very interesting that different problems in different fields tend to have some answer that is connected. So in nanomaterials, the minimum energy state of a ferromagnetic material is frustration index. In biology, we have decomposition of a biological network to monotone subsystems, and the number of these subsystems is frustration index. In finance, a portfolio of securities can be managed by calculating frustration index, and in electronics, the number of phase conflicts in integrated circuit design is frustration index. And it's strange to me that this value has never been, this measure has never been studied using an exact method. So to the best of my knowledge, there was no way to calculate this measure exactly. And we're going to use a mathematical programming model to find it. So here is a quadratic model. We simply put the frustration f of ij as the objective value, as the objective function, and we don't have any constraints, so it's an unconstrained binary quadratic programming model. We also developed 3 binary linear models and several speed-up techniques. We analyzed 10 different data sets, so this is the well-studied data set of New Guinean tribes and their positive and negative interactions. Each node represents a tribe, and we have edges representing alliance of these tribes or antagonism between them. So the frustration index for this network is 7, while if we reshuffle the signs on the preserving for the structure, we get something around 15. So this network is unbalanced, but compared to what we expect by chance, it is much closer to balance than what we expect by chance. So we do the same analysis for the 4th time frame of Samson data set. Frustration is 5, which is smaller than that of the reshuffled network. We also analyze it for a network of college boys, a network of college girls. We have a network of US senators inferred by Zachary Neal based on Fowler's dataset. So in here, green edges represent positive relationships between senators based on their voting behavior. Negative edges represents antagonism between these senators, and we can see that the frustration index is smaller than what we expect for what we have for the reshuffled network. Here is a biological network with hundreds of nodes and edges. For this one, the frustration index is larger than what we have for the reshuffled network. In other biological network, we have molecular interaction map of macrophage with thousands of edges. So as the problem is NP hard, it's really difficult to find the exact solution. But interestingly, our linear models are capable of processing graphs of this size and order in a split second. Here is a gene regulatory network of something that I cannot even pronounce. I've heard of yeast, but again, we have thousands of edges, and the value of frustration index is much smaller than the reshuffled version. And this is the gene regulatory network of a bacterium with 3,000 edges, and the frustration index is 371, much smaller than the reshuffled version. So the main question is whether these networks are closer to balance than what we expect by chance. We use z-scores to answer this question. So if we compare the z-scores to the standard range of -3 and 3, we can see that graphs G1, G2, and G3 are much closer to balance. For the US senators, it is very, very close to balance relatively. G6 and G7, they are not balanced because the values of z-scores are greater than 3. And the last two biological data sets are also very close to total balance. Here is an evaluation of our model in terms of solution quality and solve time. So as there were no exact methods in the literature, we compared our work to approximation algorithms, data reduction schemes, and heuristic algorithms. So the solutions provided by these methods, we can see that they are suboptimal. Well, as there were no exact solutions to verify whether these algorithms are working, it doesn't come as a surprise. And in terms of the solve time, our model is capable of processing these graphs something around a second on an ordinary computer. Then we have a dynamic sign network of international relations between countries, which is based on the correlates of VAR data set. So this shows the positive and negative international relations between countries over time. So we start with 1946 in here, and as we move forward in time, there are new positive and negative international relations between countries. We can see that there are new formal alliances being formed between countries, as well as formal enmities. So now it's interesting to see whether these changes in half a century of international relations represents going towards balance or going away from balance. And we're going to use the frustration index to answer this question. I'm not sure whether the color are distinctive, but green colors represent formal alliances, and red edges represent enmity between these countries. So that's 1996, and here is the frustration index over time for this network. As the number of edges change in different time steps of this data, we need to normalize the frustration index. And when we use the normalized version, we can see that the international relations of these countries is going towards balance. So if we get to the point where f of g is 1, it means the total bipolarization of the countries, where we have two groups of countries with positive edges between them and negative edges in between, which I'm not sure whether it's something that we want, but the data shows that we are going in that direction. So in terms of extensions, if we consider a weighted sign graph, that would be another interesting question. And we can consider more than two colors, which is essentially the generalized balance theory or weak balance, David's definition, and it's called the correlation clustering problem, which is a well-studied problem in operations research. So I think we have quite a few minutes for question and answers. Thank you.